Zoos give people opportunities to learn about the protection of animals, their habitats, and adopt sustainable behaviors. Each year, 181 million people visit zoos worldwide, with most of these being children expecting educational experiences. The educational process for children at zoos, however, is nuanced, as it needs to be subtle and clever. To do this, typically zoos educate children through use of signs and more recently technologies such as interactive signs, tablet-based systems, and augmented reality mobile phone systems. While children are the most frequent user of these systems, they often engage only at a surface level without really intaking their content. Further, adults often lead children away from these activities to view the animal directly. As a consequence, zoos have changed how they employ technologies by giving animals direct access to computerized systems. While these technologies are primarily for the animal's own well-being, they have this secondary educational goals for visitors by helping them create an emotional connection and foster understanding. This in turn helps visitors learn about animals and internalize educational messaging. There is a clear need and potential for innovative education systems at zoos. However, children are typically not involved in the design of these systems that they directly use or learn from in zoos. Instead, it's commonplace for adults to be consulted exclusively, leading to a lack of child's perspective. To look at how to create better educational experiences and to understand the roles that children see for themselves, animals, technologies, and adults in zoo computer-enabled systems, we developed a participatory educational approach called ZooDesign. ZooDesign is a novel, playful design experience via a workshop which aims to support children's learning about zoo house animals while at the zoo and look at how they envision animal-involved technologies. ZooDesign consists of a card set of animal and enrichment cards, an ideation sheet with creative space, Lego and animal figures, and a role-playing activity. Animal cards included 8 zoo animals, with each having a picture of the animal, basic stats information about the animal's environment, nutritional need, social and play behaviors, along with details about the individuals housed at Caucasari Zoo. For the enrichment cards, we distilled these into child-friendly terms, again giving a definition and example on each. To use our method, we ran a workshop with 12 local children at Caucasari Zoo in Helsinki, Finland. We began with a guided tour, followed by a short drink break. We then gave the children a quick talk on animal-inclusive technologies, giving them time to ask questions and reinforcing this talk with examples at Caucasari Zoo. After this grounding, children were introduced to the rules of the game and played our ideation game. To play the game was simple. Children picked one animal and one enrichment card from our ideation set and then used the ideation sheet to envision the future. We ran this self-directed process twice, where the children were free to choose to work together, talk to each other, run around the room, or even ignore the game and play as they wished. After this game, we used the role-playing method to get casual interviews of the children who wanted to speak. For this, one of us pretended to be a reporter speaking on behalf of a wealthy billionaire who wanted to find out what children were up to and get ideas for their zoo. During this phase, children excitedly spoke about their designs to the roving reporter and free-formed new ideas. We then closed the workshop by thanking the children for attending and invited the parents to see and hear more about their creations. This workshop resulted in 22 designs. Half of these were technical and half of these were non-technical. The non-technical designs included, for example, a marmot puzzle toy. The technical systems included a variety of animals and systems. For example, for bears, there was a mat which contained different colors and tastes so that a researcher could explore what bears liked licking. One child also envisioned KitKab, a complex system which plays sea sounds to eagles and has a temperature-controlled nest and various hanging toys. Another child developed a system for boars, which was a balancing system where boars must walk up a set of steps and press a button to release food. If a boar was good at balancing, it could use such a system to release food for the rest of its boars. For camels, there was Camel Chase, which used a drone with food attached to it, where a human would control the drone and make the camel chase the food around. There was also a system for boars called Piggy Wheel and Train, which would lure a boar into a Ferris wheel with food and then give them opportunities to use the train or the wheel to see around the rest of the zoo. As you can see from the children's drawings, we found a few themes. Firstly, that the human has a clear role in these systems, but other than possibly the camel drone system, none of these involved children. The children did, however, envision the adults in future technology systems to monitor or research the animal rather than directly use a system with the animal. Further, all but one of these systems were to be used by animals alone. This indicates that children see humans and animals as having separate solitary function in zoo technology systems. Additionally, most systems were game-focused, often using tangible or button interfaces. However, the way the children saw animals interacting was varied from nose, claw, foot, tongue, and proximity-related interactions. Most of these designs were also specific to the category of enrichment envisioned. Food was typically handled in a non-technology manner, but also often used as a medium to provide wild and natural behaviors and for successful interactions to assist the animals in understanding the system and enticing them to start using the system. Overall, food and play were highly prevalent and often interwoven with other categories, suggesting that children value these categories of enrichment and that these are more self-evident for children. Reflecting on our process, the workshop activities tapped into constructionist principles, allowing children to physically represent, experiment with, and redefine their mental models of zoo-based technologies and their general understanding of individual animals in ways that are not commonly possible in zoo visits. The multimodal method allowed children to elaborate on the ideas they envisioned and reconceptualize them physically after watching them play out. This method also helped other participants and researchers alike understanding their designs. The game itself was successful in capturing and holding the children's attention, with 22 out of 24 ideation sheets completed. We put this down to our process remaining simple enough not to confuse children, with our roving reporter providing additional opportunities for social co-construction of knowledge, giving children a platform to explain their ideas, listen to others, and negotiate animal-involved technology concept with fellow participants. As a result, ZooDesign method offered rare opportunities for children to share and give views on what their ideal zoo exhibit should resemble and how they saw technologies, animals, adults, and themselves as part of the zoo. In this way, ZooDesign encouraged children to think beyond their own perspective and really gave us insights. Children frequently portrayed animals as being used by the technology to gather information, with adults as observers and active users controlling this technology. This viewpoint poses ethical problems in that technologies should do things not to individuals, but with them. And these aspects of agency and ethics are complicated in zoo contexts surrounding animals and children, where there is clear ethical concerns on both sides of the fence. This split perspective was also reflected in the different perspectives that children took when designing systems. In their creations, children had different motivations for the systems, depending on what vantage they viewed them from. Children saw researchers as using technology to collect data and learn about the animals, visitors using systems to engage with animals, and the animals being enriched by means of technology in some form, but the children themselves were totally excluded. Yet, children should undoubtedly be involved in systems designed to educate them at zoos. This creates interesting and really unanswered questions around where the center of design lies and how can zoo technology meet different stakeholder needs in these complex spaces. In summary, we ran a workshop-based study with 12 children to develop new methods for educating children at zoos and for investigating what role children see themselves taking in future zoo technologies. We did this through an imaginative participatory design approach called ZooDesign that aims to facilitate and scaffold children's learning and understanding. Overall, ZooDesign appeared successful in that most children envisioned systems that considered the animal's needs and requirements. However, the method is neither perfect nor complete, but it is a solid first step towards children actively developing technologies and leading their own educational experience in zoo contexts.